Hello, welcome back to the Philip J. Currie Dinosaur Museum Virtual Speaker Series, where we have paleontology guests call in for presentations on science, fossils, and dinosaurs, and where the public will be able to ask questions both here at the museum and live on YouTube after the talk. First off, we want to acknowledge that we are on the homeland of the many diverse First Nations and Métis peoples whose ancestors have walked this land since time immemorial. We are grateful to work, live, and learn on the traditional territory of Treaty 8. Today, we have Dr. Michael Ryan presenting on the horned dinosaurs of Canada. Dr. Ryan is a dinosaur paleontologist currently working as the Adjunct Research Professor in the Department of Earth Sciences at Carleton University in Ottawa, where he co-supervises undergraduate and graduate students. He's previously held positions as the curator and head of vertebrate paleontology at the Cleveland Museum of Natural History and the director of education and public programming at the Royal Tyrrell Museum of Paleontology. Over his career, Dr. Ryan has led or co-led expeditions in Canada, the United States, Mongolia, Greenland, South America, and Africa. In addition to authoring more than 200 research papers and conference presentations, he has described more than 20 new dinosaur and other fossil vertebrate species. His research involves the systematics, taphonomy, and paleoecology of the late Cretaceous dinosaur faunas of Western North America and Mongolia, with a specialization in the ceratopsian horned dinosaurs. His primary research is conducted through his Southern Alberta Dinosaur Project that he co-leads with Dr. David Evans from the Royal Ontario Museum and the University of Toronto. This long-term project is investigating the patterns of dinosaur evolution, ecology, and the biogeography during the late Cretaceous. The horned dinosaurs were one of the most common dinosaur groups in the late Cretaceous of North America. They range in size from the enigmatic dog-sized Gryphoceratops from the Milk River region of Alberta to the giant Triceratops that roamed across North America just prior to the great dinosaur extinction at the end of the Cretaceous. Much of our understanding of the evolution and diversity of horned dinosaurs comes from discoveries made in Alberta over the last 100 years. In today's talk, you'll learn about some of that history, some of the spectacular new horned dinosaurs named in the past 10 years, and the answer to the classic question, who would win in a battle between T-Rex and Triceratops? Thank you for tuning in, and with that, I will let Dr. Ryan take it away.
Thank you very much, Jackson, and welcome everybody watching me on YouTube. I'm going to take a moment here to share my screen and we can get started. Okay, so everybody should see my first slide, which is says Horned Dinosaurs of Canada with my name right there. So yeah, thank you, Jackson, for the great introduction. It's almost like I wrote that amazingly. So we're going to cover sort of a diverse series of topics here, all focused around horned dinosaurs. We're not going to talk about every horned dinosaur in Canada. That would take too long, but we'll hit at least some of the highlights. As Jackson mentioned, I'm a dinosaur paleontologist. I've been doing this for almost 40 years now. The majority of my work currently is being done in Southern Alberta with a great crew as part of the Southern Alberta Dinosaur Project, co-led by Dr. David Evans. We've got some great volunteers, students, and staff who help us out. I've done a variety of other things, of course. There on the bottom right, left-hand side of my screen is a shot of me in the Tunisian desert back when I was doing some work for Lucasfilm when they were getting ready to film their second Star Wars trilogy and going back to relocate the sites that they had originally filmed in Africa. And that's me posing with the actual Karat dragon from the very first movie, which made a new cameo appearance in the new Mandalorian TV show. So that's the actual skeleton of the animal, but it was fiberglass, and it was actually a model used for a previous Disney movie. So I've been fascinated with dinosaurs since I was a child, and on the right-hand side of the screen, you can see actually one of the model instructions I had when I was a kid when I put together my first Triceratops model. And surprisingly, I basically do exactly the same thing today. I find a dinosaur, and then I try to go through doing the final assembly, which means putting the head on the body, putting the legs on the body, and then putting the horns on top of the head. And that pretty much sums up my scientific career. Our story about horned dinosaurs actually begins and ends with Triceratops. Triceratops was the very last horned dinosaur to evolve and roam North America at the end of the Cretaceous, 66 million years ago. but it's also the very first horned dinosaur that was discovered in North America going back to the 1800s. And we're going to cover a little bit of that history today. Who are the horned dinosaurs? You don't need to worry about this cladogram on the left-hand side of your screen, but I just want to give you some definitions. Ceratopsia means horned face, and of course, everybody knows that there's horns over the eyes and horns on the nose of most of the horned dinosaurs. They originated back in the mid-Jurassic of Asia, and then they went right to the very end of the Cretaceous before that asteroid took out all the large non-avian dinosaurs. They range across the Northern Hemisphere, North America and Asia primarily. There's some tentative evidence that they might be present in the Southern Hemisphere, but it's problematic at the best. And generally, when we're looking at the history of horned dinosaurs, they start off as small dog-sized bipedal animals, this thing called Styracosaurus, which I've got in silhouette in the middle of my screen here. And the final members are members of the family Ceratopsidae. And I've got an example of Alberta there in the bottom, which are large quadrupedal animals with the very large skulls ornamented with the horns over the eyes and or over the nose. These are all herbivores, and they're ornithischian dinosaurs, and we believe that the vast majority, if not all, the ornithischian dinosaurs were plant eaters. So what am I going to do today? I'm going to talk a little bit about the early history of collecting horned dinosaurs and touch upon the evolving science of dinosaur paleontology. We're going to introduce and talk about specifically some of the more important horned dinosaurs. Then I'm going to talk about some of the recent work that's been done on horned dinosaurs by my colleagues working with me in the Southern Alberta Dinosaur Project. So let's start here. What do we know about the very early origins of horned dinosaurs in North America? Well, we know that the fossils of vertebrates would have been identified by the indigenous people of North America going back well before Europeans or the white man arrived in what we now have as North America. So they were very important, working with some of the early explorers, helping them navigate through the landscape when they were first looking for dinosaur fossils and helping to identify some of the first good finds. Going back, coming up forward in time, the very first scientifically named dinosaur was not a ceratopsian. It was actually a large theropod called Megalodon. It was identified by this man here, William Buckland, going back to 1824. And there on the lower left-hand side of the screen, you can see what some of the early reconstructions of dinosaurs looked like. These are the famous sculptures by Waterhouse Hawkins, which are still on display in London. Not very good representations of what we now know dinosaurs look like, but at the time they were startling. And Megalosaurus is actually the dinosaur in the background right there. The term Dinosauria and the definition of the group was actually defined by Sir Richard Owen back in 1842. He is a giant of a vertebrate anatomist and scientist who dominated the scientific field in the mid-1800s, did a lot of pioneering work on many different groups. Interestingly, he was one of the first people to identify, well, of course, what dinosaurs were, but he also suggested that they may not have been identical to the modern cold-blooded reptiles like crocodiles, alligators, and iguanas, that they probably had more in common with living birds. And he, I'm not sure if he explicitly stated that they may have been warm-blooded, but he was certainly implying that they would have had a more active physiology than their modern cousins like crocodiles. When we actually find the first evidence of horned dinosaurs, it comes from the Midwest of the United States, as this area was being opened up and surveyed to build new towns and find areas for ranchers to settle in. There was a series of surveys that were being done. In 1855, a gentleman named V.F. Hayden actually collected ceratopsian teeth from the Judith River Formation in Montana. If anybody's been to Alberta and gone to the Royal Troll Museum, if you go directly south from there and cross into Montana, you will hit rocks of the same age as you find in southern Alberta. And these are what the Badlands look like down there, very similar to what I work in southern Alberta. So Hayden is pointed out with the little white arrow there on the left-hand side, and he just found some scrappy teeth, which were later identified to belong to ceratopsians. Initially, they thought they were duck-billed dinosaurs, and some of them indeed were, but there were also some ceratopsian teeth in there. The late 1800s, for almost 30 years, are dominated by two large personalities, Neil C. March and Edgar Drinker Cope. These are the two gentlemen that engaged in the famous bone wars. You can go online and learn a lot about them. I just want to point out that these are the two people that drove the discovery of dinosaurs in North America, primarily Western North America. Marsh himself wasn't wealthy, but he was fortunate in having a wealthy uncle, George Peabody, who built the Peabody Museum for Marsh and set him up as a professor of paleontology. Cope came from a moneyed family. He settled in Philadelphia at the academy, and the two of them initially were friends, actually cooperated in some scientific research, but very quickly became antagonistic enemies, and their two competing crews are legendary for the shenanigans they got up to. But between them, they named hundreds of new dinosaur specimens. And Marsh is going to be the one that will, or Cope and Marsh are both have important roles to play in horned dinosaur history. So the first good skeleton of a horned dinosaur was found in 1872. It's that there's an illustration there on the right-hand side. It was named by Cope as Agathamus. We now know this was probably a Triceratops, maybe Torosaurus, but from the rocks that it was found in the Western United States, they're the only large-bodied ceratopsid there would either be Torosaurus or Triceratops, so likely a Triceratops specimen. The next year in 1883, there is another horned dinosaur named Paleontologist, which is no longer valid, but again, probably a partial fragmentary ceratopsian skeleton. You look at this drawer full of broken bones and you go, how do you know this is even a dinosaur, let alone a ceratopsian? Well, as paleontologists, we're vertebrate anatomists, so we spend a lot of time learning and understanding the skeletons of a wide variety of vertebrate animals, from fish to mammals and reptiles and everything in between. And if you specialize in one group of dinosaurs, you've looked at every bone from every part of the body, and you can identify small fragments. So for a ceratopsian paleontologist, it's relatively easy to look at this material and say it's from a large-bodied ceratopsid. And when you actually know the area and rocks it was being collected from, you put two and two together, and it's probably a Triceratops. I work on the other group of horned dinosaurs that belong to the Centrosaurs, and we'll define these two groups in a couple of minutes. But the first good evidence of Centrosaurian ceratopsians comes in 1876. A gentleman named C.H. Sternberg, who will factor into some discoveries later that we'll talk about, was working for Cope and found a whole bunch of enigmatic material, partial skulls and skull fragments that myself and colleagues are actually still working on to this very day. This animal, which was known as Monoclonius recurvicornis here in the lower left, is something that is actually an active part of a new dinosaur that I'm describing with David Evans and some of our colleagues based upon the work that we've been doing in Alberta. The person who really kick-started ceratopsian paleontology is this gentleman, John Bell Hatcher. He's called the grandfather of ceratopsia. So he began working with Marsh as a collector, and he collected dozens and dozens and dozens of Triceratops skulls. In fact, we didn't see as many skulls collected by any one individual until Jack Horner started his Hell Creek project about 20 years ago that focused on collecting Triceratops and T-Rex skeletons from the Hell Creek. He began writing the definitive monograph on ceratopsian, on horned dinosaurs, that would describe every bone of the body in immense detail. Unfortunately, he passed away before publication, so Marsh and his colleague Lull picked it up, and it was published in 1907. And if you're a horned dinosaur paleontologist, you still use this book. It's our Bible for horned dinosaur anatomy. I have it on my desk beside me, and I refer to it almost every time I'm writing a new paper. But by 1887, we still didn't really know much about horned dinosaurs. We're starting to find fragmentary material. And when this specimen here, these partial top of the skull with these two large brow horns sticking up, were presented to O.C. Marsh, he actually thought it was a relatively modern bison specimen. So he named it Bison altocornis. It was 2 years later that he actually realized that it was a dinosaur, not a mammal. So it just shows you how embryonic the field of horned dinosaur paleontology was, even towards the end of the 1800s. In 1889, Marsh names Triceratops, and 2 years later he names Torosaurus. Torosaurus there on the left is essentially a supersized Triceratops. It's noted for having the largest vertebrate skull of any animal, and that's primarily made up by the the large shield that comes off the back of the skull that we'll go into more detail in a few minutes. And then finally in 1890, Marsh defines Ceratopsidae, that family that includes all the horned dinosaurs that were known to that time. And I've just put a couple of key characters there that define those that you don't need to worry about. But if you were a student in one of my dinosaur classes, I would make that examination material for you. In Canada, there was also work going on horned dinosaurs. In the late 1800s into the early 1900s, Lawrence Lamb was working for what's now the Geological Survey of Canada. And he eventually named Centrosaurus, Styracosaurus, and Chasmosaurus over the first 2 decades of the 1900s. Just an immense personality who did an awful lot of really incredible work. The other group that did a lot of work in Canada were the Sternbergs. We mentioned C.H. Sternberg doing some work with Cope previously. He was the father. He had 3 sons, George, Levi, and Charlie. They were initially hired by the Canadian government to compete with the Americans who were working in the Red Deer River Valley, primarily in what's in the area that's now around Dinosaur Provincial Park, as well as up around Drumheller. They were very progressive at the time. They didn't actually want to they didn't say the Americans couldn't come in. They just hired people to collect on behalf of Canada, and they happened to be Americans. Sternberg Sr. went back to the US within a few years, but George, Levi, and Charlie all stayed in Canada for various lengths of time. Charlie actually settling in Ottawa, where I am right now, became the chief paleontologist for what's now known as the Canadian Museum of Nature. And he described an immense number of dinosaurs, including Chasmosaurus russellii, Montanaceratops, which was initially known from Montana, but is now known from Alberta. And of course, the famous Pachyrhinosaurus, which is emblematic for dinosaur paleontology in the Grand Prairie region. The genus was initially defined upon material that was collected from southern Alberta, but of course we now have the fantastic bone beds in and around the Philip J. Currie Museum. If you haven't been up there, if you're watching virtually and you haven't been to the museum, please make the effort to get up there and see their fantastic material. And finally, the Americans were actually doing work in Asia, and they found some of the most primitive types of horned dinosaurs as part of their Central Asiatic expeditions. This was a series of expeditions put together by the Natural History Museum in New York, the American Museum of Natural History, led by the famous paleontologist or paleontology popularizer, Roy Chapman Andrews. He was more of a leader than a paleontologist, but it was through his auspices that these immense expeditions went into Mongolia and China and found the first Protoceratops. They found the first Psittacosaurs, and we'll place these in a phylogenetic context in a few minutes. So by the early 1900s, we now have the basis for ceratopsian research set. We now understand the large-bodied ceratopsids through Triceratops and Torosaurus from the US. And from Mongolia, we now have an understanding of what the basal forms looked like through Psittacosaurus and Protoceratops. So let's just move in and narrow in our focus a little bit and talk about some of these various types of horned dinosaurs. I've got a little cladogram here with some of the key characters on it. You don't need to worry about this, but I will point out at the bottom left, we have the most primitive type, the Psittacosaurs, the small bipedal ones that were only a couple of meters long at their longest length. And as you move up the cladogram, you become into progressively more derived forms. And at the very top, you have Ceratopsidae, which were the last group to evolve and include Triceratops, Pachyrhinosaurus, Centrosaurus, and a few others. Some of the key features that define all of Ceratopsia are the bone called the rostral. That's a bone that forms the upper part of the beak at the front of a horned dinosaur. So if you looked at one of these horned dinosaurs in life and looked at the front of its face, it would have a pair of pointed pinchers, very much like a turtle beak. The lower part of that is the predentary bone that caps the front of the lower jaw. And there's this little unique bone called the rostral that's only found within ceratopsians. And it forms the upper part of that beak, which both parts of which would have been covered with a keratinous sheath and was probably used for nipping through very tough vegetation. On the lower part, I've got a dorsal view of one of the primitive ceratopsians, the Psittacosaur, and the jugal bone that forms the triangular part of the side of the face tends to end in a small horn, which sticks out away from the body, giving the face another horn, as in horned face for Ceratopsia. The story of horned dinosaurs is all about the evolution of that large shield or frill that comes off the back of the skull. I've got two rows of dinosaurs here. In the top row, we're looking at them in left lateral view, and then we're looking at the same skulls from directly above. On the left, we have Psittacosaurus, which is one of the most primitive ceratopsians, and on the right, we've got Triceratops, is one of the most derived. Those skulls are not to scale. You could probably fit 50 Psittacosaur skulls across the length of a Triceratops skull, so it's much smaller. But we look at the bones along the back of the skull, and we see that there's three bones, the paired scamosals and the midline parietal, which actually, through evolution, form the shelf that extends back and away from the body. The scamosals are paired. I've marked them in orange here in this illustration, and the main part of the body of that shield is made up with the blue parietal. You have exactly the same bones in your skull, and I've put a little human skull there to the far right-hand side of the screen. In humans, the bones of our skull fuse together, but they're still there. So if you put your fingers to your temples, that's a scamosal. Put your hand on the back of your head, just behind your ears, that's the parietal bones of your skull. The most basal form, the most primitive ceratopsian we have is a little animal called yinglong from the late Cretaceous of late Jurassic of China. You can see it on the lower left here. It's you're looking down at it from above, a little field jacket that's paired. The head is pointing towards the right, and the tail is coming off here to the left. You could actually cradle this little animal in your arms like a small dog. And the skull that I'm showing you here on the right-hand side of the screen is pointing towards the left. And the number 1 points to the little tiny rostral bone, that little upper beak of this little ceratopsian dinosaur that defines it as a horned dinosaur. And then the number 3 points towards the back of the skull, where we see the scamosal and the parietal bones just starting to elongate a little bit. They're not very long here, but they're definitely forming a small shelf. So we've just talked about yinglong, which would be off the bottom of my chart right here. As we move up the cladogram of ceratopsia, we've talked about psittacosaurs a couple of times. I want to show you a little bit more about them because they're interesting for a couple of facts. These things look to me like modern beavers. They would have been bipedal. They would not have had a flattened tail, but their foreshortened face with the beak at the front of it reminds me of those large incisors that come off the front of a beaver. I'm not inferring that they had any behaviors like beavers, but they were small bipedal herbivorous dinosaurs. What's really interesting about these things, if you look at their tail, in some of the beautifully preserved fossils we have coming out of China, there's a series of bristles coming off the back of the tail. These are modified scales, sometimes referred to as feather-like quills coming off the back of the tail. It's the earliest evidence we have, or some of the earliest evidence we have within the ornithischian dinosaurs of ornamentation that's not just pure flat scales on the body. And we also have good evidence that perhaps these animals were very social. We have mass accumulations of adults of these psittacosaurs in Asia. And we also have a variety of nesting sites, which are showing you a photograph there on the bottom right. So there's a whole series of small, either embryos or hatchlings. There is the skull of a large adult sitting there in that photograph, although if I remember the story correctly, this was a specimen that was purchased, and whoever sold it put this large adult psittacosaur skull in with the babies to make it a little more interesting. They could tell a story of parental behavior, but I don't think that's actually associated with the small body fossils of the psittacosaurs. As we move up into the more derived forms of ceratopsians, we move into a group called Neoceratopsia. You don't need to understand what the characters are for this, but it's everything else that's more derived than yinglong and Psittacosauridae. Which brings us to one of the very first North American ceratopsians. It's this little animal called a quillops that was found about 25 years ago in the early Cretaceous of Montana. And we know that ceratopsians evolved in Asia, but at some point they would have had to migrate to North America. And this is the first fossil evidence, the oldest fossil evidence we have in North America of a ceratopsian dinosaur. So it's from an animal very similar to a Quillops that would have evolved into the dinosaurs that form the group Leptoceratopsidae, as well as the large-bodied ceratopsids in the younger sediments. Here on the left, there's the skull. The back of the skull is on the left. The front of the skull is on the right. You can see the small rostral bone right here. This broken area would be where the orbit was, and you can see the teeth that line the maxilla as well as the premaxillary teeth right there. A very small little specimen. It's the size of a small potato. It would have fit in your hand, so not a very big animal at all. It sits quite nicely between the more primitive forms, things like the Stegosauridae, and then you can see things like Ceratopsia are actually quite far up on our phylogenetic tree here. As we move up, we move into one of the two main groups of North American ceratopsians, the Leptoceratopsidae. These are sort of bulldog or larger sized animals. These are probably animals that are going around primarily quadrupedally now. They've got large enough bodies that they're now down on their forelimbs as well as their hind limbs. They're not as large as Triceratops, for example, but they're several meters long at this point, which with much more bulkier bodies, much deeper skulls with much more developed jaw musculature to process plant material. And if you look at an individual tooth that comes out of the jaws, I've shown up here in the upper right, it's got a pretty unique notch in it, which means that the jaws weren't going just up and down. They were actually having some sliding motion from side to side. And one of the things that defines Ceratopsidae is that they've got one of the more complex sets of teeth and jaw mechanisms for processing plant food that will evolve within dinosaurs. And we're seeing the first evidence of more complex jaw mechanics within the Leptoceratopsidae. I've actually been fortunate to describe a couple of new genera of Leptoceratopsids with my colleague David Evans and some of our colleagues from the Royal Toronto Museum. A few years back, we named two new horned dinosaurs, two new Leptoceratopsids. Gryphoceratops, as Jackson mentioned, comes from the Milk River region. And then Unescoceratops actually comes from the Dinosaur Provincial Park, Dinosaur Park formation from Dinosaur Provincial Park. They were both named on one bone alone, the lower jaw. One of the dirty secrets about dinosaur paleontology is that it's relatively rare to find a complete skeleton of any new dinosaur that you're describing. You usually find fragmentary remains, or in the case of Leptoceratopsids, you're lucky to find one bone. A very common bone would be the frontal from the top of the skull or the lower jaw. So the fact that we had these two nice lower jaws, one of which that had teeth in it, allowed us to name a whole new type of dinosaur. And I've had people ask me, how can you possibly name a dinosaur on one bone? How do you even know what that animal looks like? Well, as I mentioned earlier, we're vertebrate anatomists, so we understand the anatomy of a whole variety of animals, not just dinosaurs. But within dinosaurs, every group of dinosaurs tends to have a very conservative anatomy. If you're looking at duck-billed dinosaurs or looking at horned dinosaurs, if you cut the head off the body, the postcrania, as we call it, the part of the body minus the skull, looks very similar between various genera. So within the family Leptoceratopsidae, which I've shown you a little skeleton of Leptoceratops right there on the right, the bodies all look alike. And fortunately, the skulls look very similar. And one of the more diagnostic bones, the bones that contains characters which allows you to define new type of dinosaur, is actually found within the jaws of these little Leptoceratopsids, both the size and the shape of the main bone, the dentary forming the lower jaw, as well as the size and shape of the teeth, which I won't go into details here, but the Gryphoceratops that we described from that lower jaw is the oldest ceratopsian known from Alberta. There's also been more work done on Leptoceratops fairly recently. David Evans, with one of his former postdoc students, Victoria Arbour, who's now in Victoria, BC, named this beautiful little new Leptoceratopsid a few years ago, Furosaurus. It's the first dinosaur fossil, first dinosaur species from Alberta that's actually named on relatively complete material. There's not a lot to it, part of a shoulder blade, part of the limb elements, but certainly enough here to name a new genus and species. So as we start to explore the Mesozoic rocks of British Columbia, we're finding more and more material as well. So finally, we come up to the Ceratopsidae. There are two main families within the Ceratopsidae. There's the Centrosauridae and the Chasmosauridae. The Chasmosauridae includes things like Torosaurus and Triceratops, Rhinoceratops, Cosmoceratops, and the Centrosaurs are the ones that I work on primarily. So they include Grand Prairie's Pachyrhinosaurus, Centrosaurus, Styracosaurus, and a few others. If we look at what their bodies look like, again, the bodies look very similar to one another. So the key characters that you can differentiate them are the skulls. And for large-bodied ceratopsids, members of the family Ceratopsidae, it's primarily the ornamentation on the face. So it's the size and shape of the horns over the eyes, it's the size and shape of the horn over the nose, and it's the size and shape of the ornamentation that runs around the margin of the frill, that's scamosal and parietal. We'll show you a dorsal view looking down from the top of the skull of these two different subfamilies, the Chasmosaurs on the right, Centrosaurs, or Chasmosaurs on the left, and Centrosaurs there on the right. We can see that the two scamosal bones that form the shield on Chasmosaurs are very long. So this long scamosal is a defining character of Chasmosauridae, whereas in Centrosaurs, it's much shorter. In Centrosaurs, we tend to have a whole bunch of ornamentation that runs around the margin of the frill. In this case of Styracosaurus, it's developed into long spikes. In an animal like Wendyceratops that we'll talk about in a few minutes, they're small recurved processes. These are all formed by initially by small bones that actually grow in the skin over top of the frill. And as the animal matures, these small bits of bone, which are called epiossifications, change in size and shape. They fuse to the underlying bone. As the animal matures, they take on the characteristics of what will define a genus of Centrosaurian dinosaur. So what was the ornamentation on these skulls being used for? There's been a whole variety of things that have been suggested. Initially, they were thought to be defensive. When you have a large shield coming off the top of the skull, first thing people think about is like a shield that would have been used in a suit of armor to protect you in a battle. If you actually look at the thickness of most of the frills of the horned dinosaurs, they probably wouldn't have been very good for stopping a blow or stopping a powerful set of jaws coming down on them from a tyrannosaur. They're just too thin. In fact, many of them have large excavations in the middle of them, which would have lightened them even more. So we think that the size and shape of the frill, as well as the ornamentation coming off of it, was some sort of signaling device, either to signal between species for identification and possibly for mate identification. Perhaps a male with the most ornate ornamentation would be the one that would win a harem of females to reproduce with. We look at modern analogs for mammals. When we see the ornamentation on the skull of a caribou, as we have here in the lower left, we know that they use those in ritualistic battles where they push each other around. Perhaps things like Centrosaurus there on the lower middle, or some of the other ceratopsids may have used their ornamentation in the same way. One of the problems we have as ceratopsian paleontologists or dinosaur paleontologists, that maybe it's not a problem, but we always tend to look at mammals because they're so ubiquitous in our environment, to think of them as models for extinct animals. And dinosaurs were dinosaurs. They weren't mammals. They weren't birds. Well, some dinosaurs, of course, birds, but it's hard to use modern behavior in mammals to model what was going on in dinosaurs. So we really don't know, but it's a relatively good supposition that there was probably used for some sort of signaling and or interspecific combat. The ornamentation on the skulls would have been covered with a keratinous sheath. The keratin is the same thing that makes your fingernails or the beaks of birds. We have an example of the keratinous sheaths on the Triceratops there on the right-hand side, sort of forming a sheath that would sit over top of those horns, both over the eyes and over the nose. Very much like anybody who's been on a ranch or worked with bovids or cows knows that there's a sheath that sits over the horn on top of the skull. There's an example of a bighorn sheep there on the lower left-hand side of the skull, of the screen. And we know that the bony core actually does not mimic the exact shape of the sheath that would be on top of it. In the bighorn sheep, that sheath extends beyond the end of the bone, and it actually develops multiple curls within it. So what did the sheath on top of an animal like Triceratops look like? We just don't know. There is some evidence on some fossils of Triceratops of part of the sheath being preserved, but I don't know if we have anyone that's totally complete to the tip, giving us an idea what the very tip of this would have looked like. But certainly the sheath would have extended the length of the horn, of the bony cord that's underneath it. And at least for Triceratops, that would have been a very formidable weapon. So probably would have been used for a defensive mechanism as well as potentially a signaling mechanism. I mentioned that the ceratopsians have really complex jaw mechanics. I'm not going to get into this too much, but they've got hundreds of teeth in their jaws, so they're stacked side by side as well as deep into the jaw. Dinosaurs have continual replacement of their teeth, so as one wears out, it's being pushed up and out. In the middle of the slide here, I show you just a small section of that dental battery, as we call it, which would have been forming, and when you look at it in cross-section, as we've got here on the left, a series of shearing teeth from the upper and lower jaws that would have been really good at slicing plant material that came into its mouth. If you look at the jaws of duck-billed dinosaurs, the way that the teeth from the upper jaw and the lower jaw contact, it's more of an oblique horizontal, which suggests that there may have been more grinding going on here. But ceratopsians seem to be designed to shear through plant material. So cropping with the beak at the front, shearing with the teeth, and then that plant material would have been passed through the esophagus down to the gut. And we think that the guts were made up of large fermentatory engines full of bacteria, which would have helped dissolve and digest the food. Just because I don't know where else to throw this in, I want to talk a little bit about reproduction in eggs and ceratopsian dinosaurs. One of my goals as a ceratopsian paleontologist has been to find ceratopsian eggs, specifically to find ceratopsid eggs in North America. And we've not found them. We found eggs or eggs for almost every type of dinosaur, but not for ceratopsians. And some recent work that was published by some colleagues in the US and elsewhere suggests that the reason we're not finding eggs preserved in the fossil record is that the eggs of ceratopsians were soft, like soft-shelled turtle eggs, so that they didn't have the same calcium coating on the outer side to make it hard, which makes it very easy to preserve in the fossil record. And there is some evidence to, when you do the phylogenetic analysis and make some inferences from these, that the very earliest eggs for dinosaurs were also soft shells, and the development of a calcium layer over top of that is actually a later derivation. So I'm still looking for ceratopsian eggs. I'm not sure if I'll find them, but we are finding now some evidence for ceratopsian nests. This is a partial nest that was collected from Tugrikenshire in Mongolia a number of years ago and described by the American Museum of Natural History. And you can see a whole bunch of little embryonic protoceratops. They would have been inside their eggs, but the eggshell was not preserved in this fossil. So let's talk a little bit about some of the recent work that's been done on horned dinosaurs and talks a little bit about some of the things that I've been doing. Here are the examples in Canada of where you can find dinosaurs. Each one of those red squares identifies an area where dinosaurs have been collected. So we've got them from the East Coast, places like Parsboro, Nova Scotia. We've got them from the high Arctic. And then the majority of everything else comes from Western Canada. And when you plot this against a geographic map, the areas where you find dinosaurs are rocks which are Mesozoic, Triassic, Jurassic, or Cretaceous. And on this slide, although it's difficult to make out, you want to look at the areas that are green, from light green to dark green. And you can see that in Western Canada, there's a lot of green identified on this map. So that's where you would look for your dinosaurs, which is why we go to Alberta and British Columbia. These are a list of all known dinosaurs, I think, up to last year that have been identified and described from Canada. The Ceratopsia takes up the entire left-hand column, and you can see it makes up roughly a fifth to a quarter of all named dinosaurs from Canada. You don't need to know all these things, and we're not even going to go through all the Ceratopsian taxa there on the left, but we'll talk about a few of them. So about 20 years ago, I started a project which I dubbed the Southern Alberta Dinosaur Project. I was very interested in looking at the origins of some of the dinosaurs that are better known. And it turns out that the rocks you need to look at are from Southern Alberta, hence the name. And there's my colleague David Evans back when he was a graduate student, doing what we do every summer when we're not prevented by COVID from going out. We put on our boots and our hats and we go out and tromp around and look for dinosaurs. So the area of the province that we work in is this pink area on the lower part, just north of the Montana border and about 100 kilometers south of Medicine Hat. Dinosaur Provincial Park, which is much better known, is about 100 and 200 kilometers away from us. It's where it was the crucible of Canadian paleontology through the 1900s and where most of Canada's first dinosaurs were named. We have a really good understanding of the dinosaurs from Dinosaur Provincial Park and the Dinosaur Park Formation. And if we look at the just a schematic of the geologic rocks that we're looking at, I do most of my work in what's known as the Belly River Group. And you can see that it's got three formations in it. The foremost, the Old Man and Dinosaur Park Formation, which are sequentially younger. So the Dinosaur Park Formation is named after rocks from Dinosaur Park, where the majority of Canada's dinosaurs have been found. But if you want to understand where those dinosaurs came from, what was the evolutionary history of the dinosaurs that we find in that area, you need to look at rocks that are older, specifically the Old Man and the Foremost Formation. And those are the rocks you find really good exposed, or really well exposed along the Milk River in the southern part of the province. So that's why I initiated my project down south. This is our field camp, our tent set up in a rancher's field. Every year, Dr. Evans and I take out a full crew of graduate students, undergraduates, staff, and volunteers. We run a field camp. The field camp includes a field school where we're teaching actually a field course, myself through Carleton University and David through the University of Toronto. We make our meals in camp and then we break off into 3 or 4 different groups and spend our days collecting fossils, which we then bring back and do a little bit of field prep before we package them up and send them back to the Toronto Museum for cataloging and storage. We have dug a lot of dinosaurs up. This is one of the first things we worked on, a Brachylophosaurus, a ductile quarry from the foremost from the Old Man Formation. The people in the top slide here that are digging away diligently are trying to get down to this little brown stain, which is a Brachylophosaurus skeleton that was found by Juan Langston back in the 1950s. This is us, the same photograph here. So you can see we're kind of on the edge of a cliff, although it's not quite as bad as it looks. And we've collected very large full-bodied skeletons as well as tons of microvertebrate material and small individual elements. So in 2000, roughly before we started our project, this is what was known for horned dinosaurs from Alberta. You had Styracosaurus and Centrosaurus known from the Dinosaur Provincial Park Formation, and you had 2 species of Chasmosaurus. As of today, here's what the horned dinosaurs from that same region, those same formations are known. And this is all based upon work that's been done by the project that I'm involved with. We've talked a little bit about the Leptoceratopsids on the left-hand side of the right-hand side of the slide. I'm just going to talk about a few of the other horned dinosaurs before we wrap up here today. So the Centrosaurian ceratopsians are the ones that have the very ornate ornamentation coming off the back of the frills. I've been focusing a lot of my work on the origin of that group. So what did the very basal members of that family look like? We've got a very good understanding what the derived forms like Triceratops looked like, but what did the basal forms look like? So one of the most basal members is an animal named Medusaceratops, which I named with some colleagues a few years ago. And this is an interesting animal because it's a centrosaurian dinosaur that has large brow horns. And until this was actually discovered, we didn't know that centrosaurian dinosaurs could even have large brow horns. As it turns out, this material was collected in Montana by a commercial collecting outfit, which was sold to private collectors. So I tried to find this material in Alberta. If you cross the Montana border and for a few kilometers and come into Alberta, the rocks are the same type. They're called different names, but they're the same thing. And I was fortunate enough to find within a couple of years this beautiful skull of Albertoceratops. You can see my crew standing here in a quarry at the top of a hill. You can see the Milk River and the Milk River Valley there below it. This took us all of an hour to collect because it was in it was a very soft mudstone. And as we uncovered it, we realized that we had a large ceratopsian skull with large brow horns that was a centrosaur. So very paradigm shifting for us. We've also found some other basal forms, such as Wendyceratops, named after our good colleague Wendy Sloboda, who's found quite a few new animals, new dinosaurs, which are new to science. This made quite a splash when we uncovered it and named it a few years ago. The research was led by Dr. Evans out of the ROM, and we co-authored this together. We had to dig an extremely large hole. You can see a field photograph here on the right. It took us 2 summers just to open up the quarry. It's a low density bone bed, which is at the base of this hill. So we spent 2 years having our students and staff dig down to it so we could open up a large enough area to uncover the material, which ended up giving us the majority of a skeleton, or partial skeletons, which we put together. Wendy made some great news when she put a tattoo in her arm of the animal that was named after her. And then finally, we've got some other basal forms like the Xenoceratops, which is known primarily from the back of the frill. And again, when you're naming horned dinosaurs, you want to find the back of the frill. I've collected horned dinosaurs that have been 99% complete, 99.9% complete. We have every bone and every part of the body except for the back of the frill. And without that, I couldn't tell you what it is, because the definitive ornamentation is just not there. So when we put all our evidence together of what we have for at least Centrosaurian ceratopsians, this is a little cartoon cladogram showing the least derived to the most derived, which also coincidentally is a timeline going from the oldest here, Medusaceratops, up to the youngest, Pachyrhinosaurus. And there's some key characters that happen here. We see that the basal forms, like their cousins in the Chasmosaurians, have got large horns over the eyes, postorbital horns, and those horns are lost as you look in the more derived forms. There is a large triangular horn that comes off the back corner of the frill that is there through all these centrosaurs. And as you move from the more derived, from the more basal to the more derived, the horn core that you see, that's a large erect horn in things like Centrosaurus and Strachosaurus, becomes a long amorphous boss in things like Achillosaurus and the Pachyrhinosaurs that's been collected here in Grand Prairie. There's lots of good evidence for social behavior in horned dinosaurs. The Pipestone Creek and other bone beds in Grand Prairie have produced thousands of elements of dinosaurs. And when you find these ceratopsian dinosaurs in these kind of mass accumulations, it's really good evidence that they were probably moving in herds over time. So we bring in crews that map these bone beds. We excavate each individual element. We map it so we can produce 2D and 3D maps. And then we do a lot of work in the individual bones that come out. So here you're looking at the bones that surround the eye socket. I've identified the orbit where the eye would sit in kind of light yellow there. The tip of the horn over the eye is right there where the end of the arrow is. And when you collect enough of these bones and put them in order from smallest to largest, which is also youngest to oldest, we can look at the morphological changes that occur within these bones. So we can see the very youngest ones have and for Centrosaurus, for example, have a very small horn over the eye. The animals which would be teenagers to mature adults have a small but modest horn over the eye. And the various oldest ones lose that horn. The bone physically reabsorbs back into the body, and it actually loses that horn, which suggests to us that perhaps that's a signal that it's no longer a viable reproductive animal. We do a lot of work trying to figure out the origins of these bone beds. A scenario of mass drowning has often been suggested for why these animals would die, and we've got good evidence from the modern record that this occurs. There's some evidence in the sedimentology of these areas that there may have been sequential tsunamis which hit the nearby shoreline, which would have drowned the adjacent lands and drowned animals like centrosaurs that really probably couldn't swim too well and couldn't hold their noses too far above the ground. This is an example of modern caribou that died en masse in northern Quebec back in the 1980s. So whether you're looking at these kinds of examples in North America or animals in Africa, large mammals die en masse. And if this had been something in the Cretaceous or the Mesozoic, there's a possibility that these may have actually entered the fossil record. Just touching briefly on the Chasmosaurine ceratopsians, they tend to have less ornamentation off the back of their frills. We've done some really interesting work on the animal known as Chasmosaurus. There are two species of these, Chasmosaurus belli and russelli. We had initially named Chasmosaurus urbanensis, which got renamed as a new genus a few years after we named it in the literature. And we now have a really good evidence of where these things sit in the stratigraphic record. I'm not going to talk about this a lot, but being able to identify where each individual skeleton and skull comes from in the fossil record allows us to build some hypotheses of evolutionary theories. And it's been suggested we may be looking at what's known as anagenetic evolution, or slow modified change of one animal to another within this lineage of chasmosaurs. We've also have evidence of beautiful little juvenile dinosaurs. This is a specimen I described with Clive Coy, Robert Holmes, and Phil Curry from the University of Alberta. It's perfect except for the fact that it's missing its forelimbs. There's actually skin impression on the side of the body, which you can't see very well here. But importantly, you can see that we've got a complete skull and complete frill. But because this is a juvenile and the ornamentation has not been well developed, we don't know what species it is. We know it's Chasmosaurus, but we don't know whether it's Chasmosaurus belli or Chasmosaurus russelli. We do have evidence for some relatively ornate ornamentation in some Chasmosaurines. Reproduction, which was named by Caleb Brown and Don Henderson from the Toronto Museum a few years ago, has got very large ossifications, epiossifications coming off the back of the frill in a way similar to what we would see in the Centrosaurians. The skull became famous when it was dubbed Hellboy, when Hellboy was making the rounds in the movie theaters back then. And then finally, it brings us back to the very last horned dinosaur to evolve, Triceratops. Triceratops was the last and the largest of the ceratopsians. It existed on a landscape with the largest and last of the Tyrannosaurs, Tyrannosaurus rex. So if you were a large-bodied Tyrannosaurus rex looking for a meal, your best bet was a large Triceratops. It wouldn't be an easy meal, though, because those long horns on the front of the face of Triceratops would be a very good deterrent. So inevitably, I can envision that there were multiple occurrences where Triceratops and T-Rex would have faced off against each other. T-Rex looking for a meal, Triceratops looking not to be eaten. Who would win? I told you I would tell you, but actually I don't know. We have good evidence of Triceratops skeletons which have been bitten into by T-Rex. Their teeth are powerful enough to actually puncture the bone of the skeleton and the frill. But whether that was an animal that died during battle or whether it was something being scavenged by T-Rex, we just don't know. And with that, I thank you for your time. I ran a little bit longer than I wanted to, but I'm going to turn it back over to Jackson, and I'm happy to answer any questions you may have.
Thank you, Michael. That was a really interesting talk. And yeah,
very, very fast talk.
Yeah, it was fast, but I learned a lot. I'm sure our audience did too. I'm going
to just stop sharing my screen here, Jackson, so I can see you. Okay, there we go.
So if you've got a few minutes for a question and answer.
I do.
All right. Let's see some of the early questions. Based on knowledge, there are two separate groups of ceratopsians. What could we use as modern analogs of dinosaurs like Triceratops, Chasmosaurus, and the Centrosaurs?
So what would be modern analogs of those dinosaurs? Is that the question?
I believe so.
So we really don't have modern analogs for these things. These are large reptiles, non-avian dinosaurs, and their closest relatives are modern birds as well as crocodiles. So living birds are dinosaurs, and the nearest living clade of vertebrates that are related to those extinct dinosaurs would be crocodiles, but neither one of those are really good models for things like ceratopsians. When you look at large mammals that have horns on their skulls, people immediately think about rhinoceros. But did they behave like rhinoceros? I don't know. We've got really good evidence that the Centrosaurine ceratopsians moved in large herds, and most rhinos are solitary. We've got in the Hell Creek Formation and the Lance Formation of the end of the Mesozoic, Triceratops skeletons are really common, but we don't tend to find them in accumulations. There's a couple of evidence where you may find 2 or 3 skeletons or parts of skeletons together, but most of the fossils are found as solitary remains. So maybe the Triceratops and Torosaurus had a lifestyle more similar to rhinos, where they were more solitary for most of their life. We just don't know. It's a good question for a graduate student to work on.
Yeah, that actually ties really good into a question I had personally, is why some ceratopsians are found in big, huge bone beds like Pachyrhinosaurus, like Centrosaurus, and then why are some found basically individually?
It's a good question, Jackson. It appears that the ceratopsian, the Centrosaurian dinosaurs, whatever their behaviors were, brought them together in large groups for part of the year. So we've got really good bone beds for Centrosaurus, Strachosaurus, Pachyrhinosaurus. There's some evidence in the Chelosaurus, Ionosaurus, that they're also from bone beds, that these things may have had a pack or herd behavior. The Chasmosaurian dinosaurs, Chasmosaurus, Anchiceratops, Triceratops, are found less frequently in bone beds. There's a large Gryphoceratops bone bed from Texas. In Drumheller, there's a couple of multigeneric bone beds which have a lot of, I believe it's Anchiceratops-like material in it, but they're not monodominant bone beds. So there appears to have been an absolute behavioral difference between the 2 groups of horned dinosaurs, the 2 large-bodied groups of horned dinosaurs.
Makes sense. Question, is Monoclonius a valid taxon or not currently?
That's a good question. So if you read my papers, at least the early papers that I've been involved with, it's not. But I will tell you that the holotype of Monoclonius, Monoclonius lowii, is interesting. So Monoclonius is a large horned dinosaur. I didn't include it in my talk, unfortunately, but the holotype has a large skull. It's as large as Strachosaurus, but it has no ornamentation along the margin of its frill. It's got no horns over its eyes, has only a modest horn over its nose, and the back margin of the frill doesn't have any epiossifications on it. And of interest is that the horn on the nose, it's formed by an outgrowth of the nasal bone. And there are 2 nasal bones that meet at the midline, and then they fuse together to form one unit, which forms that ornamentation. The meeting halves of the horn of the nasal on Monoclonius are infused, which suggests that it's still a juvenile characteristic within this very large-bodied animal. So there is something going on with the holotype of Monoclonius, which myself and other people are trying to work out, but we need to find more material. So it may turn out that Monoclonius lowii, the holotype of Monoclonius, may be a distinct genera, but at the moment we can't distinguish it from other juvenile centrosaurians. Stay tuned.
Okay, that again relates to another question we have. How do you tell the different growth stages of ceratopsians? And relating that to another question, there is some debate about Triceratops, Torosaurus being same species, different growth stages. Are they separate or the same? And then how do you tell that growth stage between different species?
Sure, great. That's a great nested series of questions there. So you tell the growth stages of horned dinosaurs by looking at dinosaurs of different sizes. So bone beds are really good. Even though the animals tend to be disarticulated in bone beds, we can get a really good accumulation of almost every bone of the body, from small hatchling-sized dinosaurs to large mature adults. And when you do the histology on the bones of those individual of different sized animals, the histology tends to support that larger bones are older. They come from older individuals, which are more mature. So you can look at the shape changes, the morphological shape changes that occur within different bones as the animal gets larger, from small hatchling to large adult. The body bones, like the arm bones and the leg bones, the vertebrae of the skeleton tend to be isometric. They don't tend to change much in shape, but the bones of the skull and certainly the ornamentation does. So you can actually map how those bones change shape, which gets us to the question about, is Torosaurus Triceratops? So there aren't as many Torosaur skulls that are known as Triceratops. There are very few. So it's like 1 to 100. We've got a really good understanding of what Triceratops skulls look like from small juveniles to old adults. And then people like Jack Horner and his former student John Scannell have suggested that Torosaurus, the larger Torosaurus skull, is actually the next stage up, a more mature Triceratops. It's a great story, and I hope that it turns out to be true, but there are some issues with it. I mentioned several times that those epiossifications, those bones that fuse along the margin of the frill, can be diagnostic for species. If you just find some of those, you know exactly what species you've got. So we know that Triceratops has those epiossifications along the margin of its frill, as does Torosaurus. But the problem is Torosaurus is a different number than Triceratops. And we do know that within all the horned dinosaurs we looked at, that the number of epiossifications you're born with is the number that you die with. They can get larger, they can change their shape, but they don't increase in number. And so there's a discontinuity between the number along the margin of Triceratops and Torosaurus. So that could just be a factor of not having enough, not knowing the variation within the skulls of Torosaurus. But to me, that raises a question mark. So I'm not discounting it, but I want to see more evidence for it.
Okay, all right. Let's see. Oh, there was a question earlier about Leptoceratops. Why were ceratopsians like Protoceratops and Leptoceratops small and Triceratops and others large? Were there selective pressures in Asia compared to North America that were different?
Why does anything evolve in the way it does? We don't know. We weren't there at the time, so we can't look at what was happening. So we know that ceratopsians evolved. They originated in the fossil record as small-bodied, bipedal, herbivorous dinosaurs like Psittacosaurus and Yinlong. They got progressively larger throughout their evolutionary history. It appears that the Leptoceratopsidae probably evolved in North America. The earliest examples we've got is Aquilops. And then from that group of dinosaurs, we probably had the large-bodied ceratopsids evolve, although we don't have the exact intermediates there. And then at the latest Cretaceous, it appears that some of the Leptoceratopsids, as well as some of the ceratopsids, migrated back into Asia. But why did the Leptoceratopsids stay relatively small compared to the larger-bodied Triceratops? We don't know. There is one species, one genus of Leptoceratopsid called Dinosaurus, which is known from Asia, that is actually the size of a centrosaur. It's a really large-bodied Leptoceratopsid. So it's not universally true that Leptoceratopsids are small compared to the ceratopsians. And when you look within Ceratopsidae, the Centrosaurine ceratopsians and most Chasmosaurs are roughly the same body size. But then when you move to the end of the Mesozoic, to the very end of the Maastrichtian, and you get Triceratops and Torosaurus, those body size are almost a magnitude larger than all the things that come before it. Why is that? We just don't know.
Good answer.
Thanks, Jackson.
Let's see. Would studying modern day horn cores and their keratinous sheaths give any insight about ceratopsian horn sheaths?
Yes, indeed. In fact, there's people working on it even as we speak. My former advisor, Dr. Tony Russell from the University of Calgary, had a master's student, Ben Borkovic, who now works for the Trail Museum, who did his master's on that. Ben, you need to publish that paper, publish your research. And so using modern analogs are a good way to build hypothesis. Sometimes it's hard to test it because we're looking at mammals versus reptiles, but at least we have a better understanding now of what is going on within both the growth trajectory of modern mammals as well as the variety of shapes that we see compared to the bony horn cores of what those horns would look like. So that gives us a little bit more of an understanding of what ceratopsians may have been able to do. There's been some really nice work done by Dr. Larry Whitmar's lab out of Athens, Ohio, looking at the bone histology and the morphological shape of things like Pachyrhinosaurus, trying to figure out what did that large boss over the nose and over the eyes, what was it for? And there is some suggestion that there may have been a large keratinous something on top of that. Some people have modeled it like the drooping horns of a muskox. Some have modeled it like a large rhinoceros-like horn. We don't know, but the suggestion is that biologically and morphologically and histologically, it could have supported some sort of ornamentation that was made out of just pure keratin.
Okay. Do you have a few more minutes for 4 or 5 more questions?
My time is your time, Jackson. I'm happy
Awesome.
to chat.
Okay, because there's more questions coming in. Let's see, really. Where would the quadratojugal be located in the ceratopsid skull? Didn't see it in the diagrams.
Okay, well, somebody's paying very close attention to their anatomy. So quadratojugal would fit between the jugal and the quadrate, just as the bone suggests. It's a spacer element. So the quadrate, if you're looking at a ceratopsian dinosaur from the, so if you're looking at a ceratopsian dinosaur from the side, the bone that forms the lower margin of the orbit, it forms kind of the cheek region is the jugal, and the tip of that is often expanded into a small horn-like or hornlet. And then behind that you can't see is the quadrate, which comes off the skull, and the quadrate articulates with the lower jaw to allow the jaws to move up and down. And there's a spacer element between the jugal and the quadrate that's called a quadratojugal. The position of the quadratojugal and the ability to see it from the side of the skull has been used to help define some, has been used as a character to define some types of horned dinosaurs.
Okay. Let's see. How can you tell a new species or separate species of ceratopsian from small pieces of bone, like if you only dig up a fragmented semi-complete skull?
Because I am that good, basically boils down to that. Just appeal to my authority as a great paleontologist, and you're going to be right. So it comes back to being a really good vertebrate anatomist. So understanding the wide variation of what individual bones look like on all kinds of different vertebrates, from their most juvenile form to their most adult form, and looking at just looking at hundreds and hundreds of bones in museum collections if you're a dinosaur paleontologist. I think I've seen almost every ceratopsian bone that is available to look at in almost every museum around the world. I mean, I've spent that much time looking at these things. And unfortunately, a lot of the bones are not complete. A lot of them are fragmentary. They were broken either prior to fossilization or afterwards, because the bones were being tumbled around in whatever river system was depositing them before they were fossilized. Sometimes they get weathered out and you only find part of it. So you have to be you have to look at lots, hundreds, if not thousands of elements, and be able to identify them from broken fragments. So it's at the point now where I can work in a large bone bed, and you can give me a fragment of a bone, and I can probably tell you what bone it is. And if it's a fragment of a skull bone, I can probably tell you the relative age of the animal was when it died. So it's knowing your anatomy and just spending hundreds of hours looking at all the material. That's how we can identify this material. And because we've done this, and if we look at evidence from bone beds where you're looking at hundreds of elements, it shows you the shape variation that is available within a population. And if you find an element that is like several standard deviations outside of what you expect from normal normal variation within that element, then you can say this is probably something that identifies a new animal. Dr. Evans and I actually described a new horned dinosaur a few years ago, which we called Gryphoceratops. And again, based on one bone, the large scamosal from the side of the face, we had found a specimen from Montana that had a very unique shape. And we thought, this is like nothing else we've ever seen in a horned dinosaur before. If we, based upon this, it seems like it's a new dinosaur. But we thought, well, maybe it's pathological. And then I was doing some work in Dr. Philip Curry's lab at the University of Alberta, and one of his volunteer technicians showed me a bone that she was preparing, and it was identical to what we had seen from Montana, even though it was in a different formation and a slightly different time. And we thought, okay, we now have two examples of this scamosal bone from a horned dinosaur, Chasmosaurian horned dinosaur. It can't just be individual. It can't be a pathology. It's got to be something real. So based upon those two elements from two different formations of relatively the same time, we could describe a new dinosaur.
All right. The question about Achyloceratops, was it, heard it was somewhat related to Ionoceratops and possibly an ancestor of Pachyrhinosaurus?
Right. Yeah. So there's actually, if you're interested, there's a paper which I published with Dr. David Evans again, and a student from Montana, Jack Wilson, describing a new horned dinosaur, came out in early 2000 called Stellosaurus. And it's actually, in that paper, we look at Achillosaurus, Ionosaurus, and Pachyrhinosaurus, as well as Strachosaurus. They form sort of a subclade within Centrosaurian dinosaurs. And we make an argument that there's actually a direct morphological, a direct evolutionary change that occurs from one to the other. So you're right, Ionosaurus and Achillosaurus do appear to be very closely related to one another, and potentially people like Jack Horner would argue that one is actually evolving into the other, and eventually those evolve, or one of those will evolve into Pachyrhinosaurus. So if you're on Google, Google Stellosaurus and read the paper that we published.
Subtle plug for your research.
I mean, all I can do is point you to the literature. If you use Google Scholar as opposed to Google, usually you can find a PDF that you can download and get it. If not, you can contact me through Jackson and the Philip J. Currie Museum, and I'm happy to send you a PDF.
Yep, very happy to arrange that. Another relationship question. What's your current suspicion on how Centrosaurus was replaced by Styracosaurus in Dinosaur Park?
So if you look at the distribution of fossils within Dinosaur Provincial Park, within the Dinosaur Park formation, it appears that there is that Strachosaurus is found only in the upper part of the formation, and Centrosaurus is found only in the bottom part of the formation. There's a couple of problematic specimens, which I'll admit, but it appears that there is a discontinuity between the two, so that Dr. Caleb Brown at the Royal Toronto Museum for his PhD work actually looked at the morphological variation within those two dinosaurs, and he found that within the zone where we find Centrosaurus, there was no discernible variation between Centrosaurus found at the bottom part of the formation to where its last occurrence is, and similarly from the first occurrence of Strachosaurus to its last occurrence, it appears that there's no directed morphological variation within that. So it appears that one is replaced by the other. Was it a direct evolutionary sequence from one to the other? Hard to say. We're looking at a transgressive series of sediments within that part of the formation. So it's quite possible that Centrosaurus was pushed out of an area that it was living in and then replaced by Strachosaurus, which was living in a more marginal, closer to the Western Interior Seaway margin. Work is ongoing on that question.
Well, I look forward to the answer to that question. So what are your thoughts on ceratopsid regional endemism? Are Chasmosaurians and Centrosaurians found in different depositional environments?
The best evidence we have is a no, although it's not definitive. When you look at where we find fossils, we find when you look at the sedimentary packages that contain Centrosaurians as well as Chasmosaurians, it's kind of random. We find skeletons of both within fine-grained muds. We find them within sandstones. We do tend to find more Centrosaurian bone beds than we find Chasmosaurian bone beds. So our database is kind of overwhelmed with specimens from the Chasmosaurians, but I just don't know. I don't know. And so one of the things we don't know about ceratopsian bone beds, Centrosaurian bone beds, is what time of the year did they form? Was there something seasonal that was going on that brought them together at one time of the year? Perhaps, they're getting together. Maybe they were solitary for the majority of the year, then they came together to mate or to rear young in a rookery type situation. And for whatever, then there was some catastrophe that caused them to die and be fossilized. And maybe the Chasmosaurians also did the same thing, but we just don't have an example of when they came together. So there's all kinds of questions which we're still working on. We're looking at teeth that are collected from microvertebrate localities. We have a lot of teeth within microvertebrate localities, but unfortunately we can't tell Chasmosaurian teeth from Centrosaurian teeth. So we're still trying to parse out that bit of data to see if that's going to help us answer questions like this one.
All right. If a Triceratops were to encounter a T-Rex, would the T-Rex be smart enough to bite off the frill or the horns with those teeth? And that relates to another question we had about puncture marks and skulls of ceratopsian. Does that relate to intra or interspecific combat use of horns?
So lots of questions in there. So I don't know what a T-Rex would do. Um, a really smart T-Rex is not going to attack a full-grown, healthy, mature Triceratops. I think it's just too darn dangerous. You've got something the size of a tank with 2 meter long horns coming off the front of the face. You are in for some serious damage if you don't know what you're doing. So if you look at modern large predators like lions, they will attack when they need to, but they're quite happy to scavenge when they can. And I imagine T-Rex is very similar. If it could scavenge something or scare away meal from a smaller predator or even a smaller tyrannosaur, it's going to do that. Because anytime you attack a living animal, you can get damaged. Everybody can go on YouTube and look at videos of lions trying to take down a water buffalo and getting kicked in the head and killed. So it's very dangerous to attack a large, healthy animal. We do have evidence of bite marks in Triceratops skeletons, but we don't know whether those occurred during a battle or whether that was just scavenging behavior. There are tooth marks on Tyrannosaur skulls, and were those happening during interspecific combats? We don't know. But we do know that within large predatory animals, when they're coming together to fight over mates or trying to determine who's going to mate, because predatory animals, the main way they manipulate their environment is with their mouths. So that's how they're going to interact. And so mouth-on-mouth contact within a ritualistic battle is probably occurred. Did they bite each other? Probably. But I don't know enough about the literature, and I haven't done any work on this, looking at the number of reheal marks on skulls and how that relates to the shape of the inflicted damage, and were they teeth or were they lesions from something else? Darren Tankey from the Royal Toronto Museum has done a lot of work on this and published a lot of papers with co-authors. So I would point you to some of his research.
Thank you. Let's see. Last week we had Dr. Friolo talking about hadrosaur tracks from Alaska, and it got me wondering, do we have any ceratopsian track evidence?
There is some evidence of ceratopsian tracks, but not in the same way that Tony described. Tony's got these multiple tracks which run side by side, and you can do all kinds of cool, biomechanics on these things. The material that's known for horned dinosaurs is it exists, but there aren't any large trackways. I've never worked on them myself, so I can't really speak to it.
Okay. Let's see. Why do we only seem to find ceratopsians and their relatives on North America and Asia? Why don't we find them in other continents?
Another good question. So it appears that they just, whatever their behaviors were and their evolutionary patterns were, they just didn't penetrate into South America and into Africa. One of the things you need to look at, the large bodied ceratopsids anyways are evolving at the very end of the Cretaceous. And by this point, Pangaea and Gondwana have broken up, and the continents are pretty much in their modern positions. There would have been ephemeral contacts between Asia and North America through the Bering Land Bridge throughout the late Cretaceous, and that's how we think some of the ceratopsians got back and forth. There's also evidence of Leptoceratopsids in Europe from like the early Cretaceous. They're just teeth, though, unfortunately, and so we don't know, are they coming over the pole? Are they coming from Asia towards North America or vice versa? And there is no good evidence for ceratopsians in Africa or South America. There is some putative material that's been named actually from Australia, but that stuff is still enigmatic. And I'm actually working on a project with some of my Australian colleagues to try to definitively say whether that's ceratopsian or not. So whatever environments they preserved and whatever sort of evolutionary patterns they were following just didn't seem to allow them to make it into the Southern Hemisphere.
Okay, thank you. All right, I don't see any other questions coming in from our audience, but one question we ask every speaker is, what's your favorite dinosaur?
That is a good question, which I don't have a good answer for. I can tell you that I've worked a lot on horned dinosaurs like Centrosaurus, so that would be the obvious dinosaur to say. But I must say that I'm sympathetic to Stegosaurus. When I was 5 years old, I watched the original movie King Kong, 1933, best movie ever made. And the first large animal you see on that's not King Kong is a dinosaur, it's Stegosaurus. And as soon as I saw that, I knew that I wanted a job that would take me to a place that I could find dinosaurs. And that's what I've done with my career. I basically followed my 5-year-old muse.
I can understand that, and I'm pretty sure many paleontologists would say a similar thing. Well,
A lot of us were inspired by something they saw when they were kids, either a book that was read to them or they read, or something they saw on television. Or for the younger generation of paleontologists, a lot of them were inspired by the first Jurassic Park movie that came out in the early 90s.
or The Land Before Time is a classic.
Another good one, a lot of my young students grew up watching Land Before Time, and it's a perennial movie. No matter what generation you're from, it's still a great kids movie.
Okay, well, I don't see any other questions coming in, and it's been quite a very lengthy presentation, but I super enjoyed it. We've learned a lot. I'd like to thank Dr. Ryan for coming in today. And with that, we'll conclude our talk. Stay tuned to our social media accounts and website for information on our next speaker series, which should be coming out shortly. Thank you and have a great day.
Thanks for your invite, Jackson. Take care.
You too.